In this video, we're going to focus on something called angular momentum. For starters, we know that an object that is moving has linear momentum. Therefore, an object that's rotating has what we call angular momentum. We know linear momentum can be found using the equation P equals mv, where P is the linear momentum, m is mass, and v is a linear velocity. Linear momentum has a direction, and it's the same direction as an object's linear velocity. Similarly, angular momentum can be found with an equation that says L equals I times omega, where L is the angular momentum, I is the moment of inertia, which we've learned previously is kind of like the rotational equivalent of mass, and omega is the angular velocity. Angular momentum also has a direction. For the purposes of our class, we'll use clockwise or counterclockwise, and the direction of our angular momentum will be the same as the direction of the angular velocity. The units we can tell from our equation, I has units of kilogram meters squared, and omega is radians per second, and so the units are kilogram meter squared per second. There's a typo here. It should say per second, not per second squared. The direction is either clockwise or counterclockwise, as I've previously mentioned. And an important concept that we learned with linear momentum was that linear momentum is conserved. Similarly, angular momentum is conserved for an object as long as there's no external force causing a torque on our object. That idea of angular momentum being conserved explains a lot about why the rotation rate changes when someone pulls their arms in, for example, or possibly if something were to happen to join a rotating object, like if someone were jumping onto an already rotating merry-go-round. We'll discuss more of this in class.